So hello and welcome to my questions and answers show. I'm Fraser Cain, publisher of Universe Today, and this is your chance to ask me questions about space and astronomy. So if you're watching this live, go ahead, post your questions in the live chat. If you're watching this after, you can post questions, you can send me email, you can post on the YouTube comments, you can post in Patreon, set up a Discord server, you can post there, so there'll be lots of places for you to send us questions. So Joe asks, even though we don't know what caused the Big Bang, did dark energy cause the Big Bang and it is accelerating the universe outwards because there is less gravity once they're farther apart? What's causing the universe to expand is two parts. Whatever caused the Big Bang, and again, we don't know what caused the Big Bang. What is the underlying event that brought all of the matter and energy into existence, and then what caused all of that to expand outward at this incredibly rapid rate? We don't know what the underlying source of that was, but we do know that it happened. And we also know that essentially the expansion of the universe is driven by two things. It's driven by essentially the leftover momentum of whatever was that original expanding event. So the universe, the Big Bang happened, and it's like a kick, a bang, that is causing this expansion. But again, it's not an explosion, it's an expansion in all places that's going on. And left to its own devices, the universe would keep on coasting. It's kind of like, I don't know, like you roll a car, you drive a car really fast, and then you take your foot off the accelerator and the car just rolls and it slows down and it slows down and it slows down. And eventually it comes to a halt. And that's what would happen to the universe. And this was one of the big questions that astronomers asked themselves 20-ish, 25 years ago was, based on this original expansion, and then you've got the mutual gravity of all these galaxies, are they going to sort of expand away from each other forever? Or will the mutual gravity eventually slow them all to a halt, and then they'll all start kind of crunching down into bigger and bigger clusters until eventually you've essentially got the entire observable universe falling in to one spot. And so astronomers went and they did this survey, and they were looking at type 1a supernovae, which are sort of considered the standard candle, a way to determine sort of a standard distance to everything in the universe. And the big surprise, of course, was not only could they not measure that the universe was slowing to a halt in its expansion, but in fact, it was speeding up in its expansion. It was accelerating. And this is completely not what anybody's expecting. It's sort of the analogy that I always like to give is like you take a ball, you throw the ball up into the air, you expect the ball is going to come back down into your hand, right? And then that tells you, and that was sort of one possibility. And the other possibilities is that you throw the ball up into the air, it would go off into space and it would sort of fly away from space, slowing down. And eventually it would get, it would coast to a halt exactly at the point where it wasn't going to fall back toward the earth and it wasn't going to fly away. Or you could throw it so hard that it would just never come back to the earth. And what they found is you throw the ball and the ball immediately just starts accelerating away from your hand off into the universe. And so the universe's expansion is accelerating. And this is dark energy. And so the expansion of the universe is driven by the momentum left over from the Big Bang, as well as the accelerating force of the dark energy. And over time, the dark energy is going to be the thing that's completely dominant and is just pushing everything in the universe away from everything else faster and faster and faster. Live Vibe Lasers. Fraser, can you discuss the size difference between the observable universe and the unobservable universe that has crossed the cosmological horizon? I've heard the unobservable is 10 to the power of 22x in size. So the observable universe is the universe that you could observe, and you have an observable universe and I have an observable universe. They're different. My observable universe, if I'm standing to the left of you, then my observable universe is like 1 light meter away farther in one direction. So I'm seeing a little more in my direction and you're seeing a little more of the observable universe. So when we imagine this sphere around us of, 46 billion light years in all directions, that is the observable universe. It's just that everything in that region has been able to give off light that has traveled all the way to your eyeballs for you to be able to detect. And of course, as we look out into the universe, we see things as we're seeing them farther and farther away. We're seeing them earlier and earlier in time. And of course, the analogy that I always like to use is, imagine you're standing in a room, and really close to you, you've got a bunch of old people, and then middle-aged people a little farther away, and then really far away, it's just babies. And then there's nothing, because that's what it would look like to look backwards in time as you're looking farther away. And so you're always seeing this really weird thing of the universe. You're seeing backwards in time as you're seeing further away. And of course, we don't know how big the actual universe is. The observable universe is just a tiny little segment of it. Now, one possibility is the entire universe is infinite, goes on forever. And so the observable universe that we can see is, I don't know, 1 divided by infinity of the actual universe that is out there. Infinity divided by 1? Anyway, the other possibility is the universe is finite. And so it could be, as you say, it is at least much, 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 much bigger, like thousands, millions, billions of times bigger. And the way astronomers figure this out is essentially they're able to calculate the curvature of the universe. So they're able to essentially measure these gigantic triangles in space. They look at the cosmic microwave background radiation, and they measure gigantic triangles across huge chunks of the universe. And then when they look at these triangles, they're trying to measure some kind of spatial curvature that's going on that would almost tell you what is the entire size of the universe itself. If the universe just went on, when would it wrap? And right now, from what they can tell, the real universe is so big, they can't measure the wrap, which is why then they think, well, the universe is either finite, but so big that we can't measure it, or it's infinite. And the jury is still out. Better and better measurements over time will either figure out how big the universe actually is, or push that minimum size to bigger and bigger amounts until eventually everyone's just going to assume, okay, fine, it's infinite. So we don't really know. I could do a whole episode where we just don't know the answer to anything. It's perfect. Jeff Wilkie asks, do more people watch your videos on YouTube or listen to the same podcasts? I get about 150,000 downloads a week on my podcast. And that's all of the episodes that we do. But typically, we're releasing about 8 episodes a month. 150,000 downloads a month. So it works out to about 12,000 listens for each new podcast. And then a few more for all of the old episodes that people are discovering. So I would say that and then on YouTube, I get about 10 to 15,000 people watching the videos. So the numbers are kind of the same, actually. We get a lot less people watching the YouTube channel these days, mostly because I'm producing a lot less content for the YouTube channel, a lot less of the original scripted episodes, and a lot more of the quality, sort of the questions and answers and the interviews. And that is a preference for me. And so I think I'll spend some time explaining that, because I know a lot of people are wondering, like, how come you don't make those guide to space videos so much anymore? And the reason is because I don't think I'm very good at it. The more you learn, the more you realize that you don't really know anything. And what I've found is interviewing experts in various fields, be it astronomers, astronauts, physicists, etc., I find that it's very useful to go right to the source, to be able to just talk to the people and say, hey, how does this work? How does that work? How does this work? And to be able to sort of piece together a picture. And it makes for content that is a lot more accurate, as opposed to me attempting to translate it from what I sort of think I understand, trying to synthesize information. And so I found, when I sort of look back at the older Guide to Space stuff, I find that although they were entertaining, and although I think people thought I did a pretty good job, to me it felt like I need to get more information directly from the source. And so I think that's sort of where my mind is at. And I'm sort of bringing you along with me. So I've found a lot of the interviews, the long form interviews that I've been doing to be really fascinating, really interesting stuff about pushing the cutting edge of space exploration and astronomy and people working on robotics and engineering and things like that. So I think that's where we're going to go a lot more. So I think that's my opinion right now. But anyway, that's why I'm trying to sort of, people have been asking me, like, why am I doing the Guide to Space? And it's like, I'm not into it. I'm really into interviewing people. So that's sort of how I feel. So Physics Police asks, will dogs have fun running in lunar gravity? First, I want to thank Physics Police for being the actual Physics Police on this channel and with me. We've had a very vigorous interaction over the years, but I always appreciate your feedback and your attempts to raise my quality and capabilities. So thank you. Will dogs have fun running in lunar gravity? We talked about this a bit in the past, that Mars gravity at like 40%, 35% is probably good enough for humans to be able to walk around and not have a hard time. But when you get down to the lunar gravity, like 15%, we've seen that the astronauts had a really hard time being able to walk around on the moon. They were falling over all the time. They weren't hurting themselves, but there was the potential to hurt themselves. So I actually think that in the beginning, when you go to the moon on your lunar holiday, you're going to have to completely relearn how to walk on the moon. It's going to take a while because there is some gravity, but not a lot of gravity. And it has all kinds of repercussions, like the amount of friction that you have when your foot is touching the ground. You have less friction, and so you'll fall a lot more easily. Something that would have been no problem walking around in socks, you're gonna have a hard time walking around. You're gonna need special kind of shoes. And so if you think of like a dog, like of course a dog will have fun doing anything, but I think in the beginning they're gonna have a really hard time. Have you ever gotten a cat and you live in a place with a carpet and your cat is just burning around, or your dog is just burning around the house really fast, they're having a great time, and then you move to a place with hardwood floors and the cat or dog just doesn't know what to do, right? They slip out as they go around corners. They completely lose it. And it's going to be like that. It's going to be really hard. I'll bet you there won't be such a thing as smooth floors on the moon. There will always be, everything will be a non-slip surface, no matter what it is that you're walking on. But of course, like, because you're going to have 1/6 the gravity, it won't hurt the same. So anyway, it's going to be funny. I like it. 25 in 30S. Why aren't we looking further past Pluto? Or taking its time, lol. I'm assuming what you mean is, why aren't we looking past Pluto in the solar system? And of course, we are. Astronomers have discovered all kinds of things in the outer solar system beyond the orbit of Pluto. In fact, it was the discovery of Eris, which is a dwarf planet that's roughly the size of Pluto, that has its own moon, Dysnomia, that caused the whole Pluto crisis in the first place. Astronomers, Mike Pluto Killer Brown was looking in the Kuiper Belt for other Kuiper Belt objects, and he found an object that was roughly the same size as Pluto. We've now learned that Eris is a little smaller, but it's much farther away from the sun than Pluto is, but it's roughly the same size. And so then the problem is, if you found an object that's the same size as Pluto, does it get to be a planet too? Don't we have a 12th planet? And in fact, what about all the other ones? Haumea and Makemake and Ceres and all these other ones that are roughly the same size too. Don't they get to be planets? And so back in like 2003, 2005, 2005, the International Astronomical Union came and had the big vote where they're like, what are we going to do about this? And they decided that Pluto was no longer a planet because we are finding all these objects. And since then, astronomers have found many more. There's the most farthest one. Oh, and I forget what it's called. It's got a really hilarious name, like, Far, Far Out? Yeah, I think it's called, there's one called Far Out, and there's one called Far, Far Out. And of course, astronomers have discovered Sedna, which is an object that at its farthest point, I think goes to like 600 astronomical units, so way farther away than Pluto. And we're right around the corner from the next great observatory that's going to be coming online, the Vera Rubin Observatory, previously known as the Large Synoptic Survey Telescope. And this one is going to be the machine that finds a zillion Kuiper Belt objects and could be the telescope that finds Planet 9, which is going to be the theorized much larger, like Neptune-sized planet that's in the outer solar system, way beyond the orbit of Pluto. So the limit of what we can find really just depends on the power of the current telescopes. And then following on with the Vera Rubin is going to be the extremely large telescope. This is a 39-meter telescope. It's going to be capable of, I feel like I talk about this every week, but it's going to be capable of viewing Earth-sized worlds directly orbiting other sun-like stars. And it will definitely be capable of taking a good look at any planets, any other objects that Vera Rubin finds in the outer solar system. So as the telescopes get better, our ability to look farther and farther out into the solar system gets better as well. Arjun asks, what interesting forms of motion would be good for exploring the moon's lava tubes? That is a great question, because we've mentioned in previous videos that the lava tubes on the surface of the moon are one of the best places for us to get, like, if you want to go to the moon, you want to get protection from space, the lava tubes are great. Once you're in the lava tube, you're completely protected by the radiation. You've got better temperature control. You've got potentially a place you can set up. You've got micrometeorite protection. They're really good places to go. And they give you a view of the history of the surface of the moon. You've got all of these samples, all this material. You've even got like lunar dust that, you know, if it's got like some kind of skylight on the top of it, then dust has been falling into this hole for a long time and stratifying in layers that you can quite easily sort of look through and see the history, not only of the moon and of the even of the Earth, of the solar system, of the universe is thought to be written in lunar dust. So these lava tubes are great, but the challenge is that they're dark. And so you can't take solar panels up to the surface of the moon. They are also potentially very rough. If you ever walked in a lava tube, they are, you know, they're not easy for wheeled vehicles to roll around. They're probably boulder filled. They probably got all kinds of material and debris. So some really interesting ideas have been proposed. There have been hoppers. So imagine some kind of, you know, multi-legged creature that can sort of flop around in low gravity with style, and be able to move itself around in this low gravity environment. There's been snake bots proposed, which would be like they look like snakes that would be able to crawl down into small crevices and be able to search and explore. So I actually think it's going to be a pretty big challenge to come up with a rover or a flying bot, something that is capable of being able to maintain power in the dark and the cold, in the extreme temperature while you're on the moon, but also be able to search these very bizarre terrain. But if it can be figured out, then it's one of the best places for a robotic mission to go. So I'm pretty excited about the idea. We'll keep you posted. One thing that's kind of interesting is the Chinese with their upcoming mission. They've got a mission that's going to an asteroid called Zhenghe in 2025, 26. And it's going to be sending a whole bunch of stuff. They're going to be sending an orbiter, they're going to be sending a lander, and they're also going to send a bunch of mini probes that are going to be going with it that will try to explore the surface, both from the ground, but also to try to kind of fly around. And so I'm sort of going to keep an idea on what they're doing with that, because I can imagine, I mean, it's a very low gravity environment, so you don't need a lot of propellant, but I can imagine a situation where you've got like a spacecraft that is using propellant to hop around on the moon in these craters to be able to explore. But again, it's fascinating. It's a great environment. We should definitely explore. Of course, the other possibility is that you just sort of have a solar panel up at the top of the skylight, and then you reel down a power cable that can then, I don't know, like, think about like the divers back in the 1800s, right? Except in this case, it's electricity, not air. Anyway, it's going to be a big challenge, and there's a lot of great projects, people working on it. I'll get some of them and interview them for you. Eric1 asks, whatever happened to the overwhelmingly large telescope? So I talked about the extremely large telescope. This is the 39-meter telescope that's being built by the European Southern Observatory. It's the follow-on telescope to the very large telescope. I know, make jokes about the name. But when they were designing the extremely large telescope, they also designed this idea of the overwhelmingly large telescope. And it was going to be a 100-meter telescope. And the gist of it was that it would essentially be the largest possible telescope that you could have on Earth, a 100-meter primary mirror. It would be incredible. And the problem was it was going to be too expensive. And so the European Southern Observatory decided they were going to build the extremely large telescope, which was only going to cost $1.3 billion. In its most recent price now, it went from 1.15 billion to 1.3 billion, but not in the bad way, like in the way where they said, let's add a bunch more functionality and capability to the observatory, which is great. By the way, they have a new website. So if you want to go check it out, do a search for the extremely large telescope. But yeah, they had originally planned the overwhelmingly large telescope to go the full 100 meters. But the problem was they were looking at the budget, and at I think it was going to be like $2 or $3 billion, they decided it was too expensive. Too expensive. And yet, of course, obviously here we are, hindsight 2020, James Webb closing in on $10 billion is going to be a 6.5 meter telescope in orbit. But, I think if you asked a lot of astronomers, would you rather have 3 overwhelmingly large telescopes or James Webb? They would take 3 overwhelmingly large telescopes. So who knows? After the extremely large telescope, maybe we will see the overwhelmingly large telescope come back online. Ground-based astronomy is getting very powerful thanks to adaptive optics, thanks to interferometry. There's a lot of great technologies that are being built into these ground-based observatories. And a lot of the technology that's being tested out in things like, say, the Very Large Telescope are going to be applied to the Extremely Large Telescope. As I mentioned earlier, it's the ELT that will be capable of seeing those Earth-sized worlds orbiting sun-like stars around other stars. So, and that's 2026. So we're just a couple of years away now from that next level of technology. Not to mention the 30-meter telescope and the Magellan telescope. So there's a lot of really interesting telescopes coming shortly within this decade. All right, so more questions in a second, but first I would like to thank our patrons. Thanks to Barry Greenway, Andrew Alexander, Gregory Donahue, Andrew Duffy, Anthony Paris, Alan Walker, and the rest of our 865 patrons for their generous support. Want our videos early with no ads? Join our community at patreon.com/universe today. Gaurav Sharma. Would building a LIGO in space increase our sensitivity to detect fainter gravitational waves? There is a LIGO in space, which is called LISA, the Laser Interferometry Space Antenna. And LISA is being built by the European Space Agency, and they've already launched one portion of it called the LISA Pathfinder. The LISA Pathfinder was one of the satellites. The eventual final LISA will be 3 satellites that will be flying in a triangle, and they will be firing laser beams, and they'll be measuring the distance of those beams very carefully as they bounce back and forth between the satellites. And then as a gravitational wave rolls over the satellites, they will expand away from each other and then contract again, and you'll be able to measure these gravitational waves. And LISA will be incredibly sensitive, especially to the kinds of gravitational waves that LIGO and other ground-based observatories aren't able to detect. And one of the big ones that astronomers they have no way to see right now are the mergers of supermassive black holes. So we can see the mergers of neutron stars, we can see the mergers of black holes, and we can see the mergers of neutron stars and black holes, and maybe white dwarfs and neutron stars, but we can't see the mergers of supermassive black holes. And I know that seems really weird, but it's because it happens too slowly. that as two supermassive, like when you've got two smaller black holes, they're buzzing around each other really quickly, incredibly massive, and they're really just sort of yanking space-time back and forth, and you create this very obvious signal that passes through the LIGO detector. But with supermassive black holes, they merge very slowly because they're so huge. I mean, they are millions, sometimes billions of times the mass of the sun. And as their event, they're going around each other, and as their event horizons merge, they are causing space-time to warp, but in this very long wave. Almost, it's the difference between, say, like ocean waves and waves in a lake or a pond. And so LISA will theoretically be capable of detecting those much longer, slower gravitational waves from merging supermassive black holes. And that'll answer really fundamental questions about what happens to supermassive black holes when galaxies collide with each other, because that's still a bit of an unknown question. One possibility, obviously, is that the supermassive black holes merge together, but there's another possibility is that they can just bounce. That even when you only have two supermassive black holes that are careening towards each other, one can bounce off the other. And I forget the exact sort of the way, it has to have a certain kind of kick, and has to have the way they have to be rotating a certain speed, etc. And so we still kind of just don't know what's actually happening. And especially if you've got like a 3 interaction with 3 supermassive black holes, I mean, there could be huge supermassive black holes just wandering the universe, and we don't know where they are. So LISA, and that's like not due for launch like in the 2030s, unfortunately. It's going to be the one that follows on for that. And then the plan is to make LISA better. So instead of having, say, just 3 observatories, you could have 12 in a great big, I don't know what you call it, 12-sided die, 20-sided die? Anyway, and so that is called the Big Bang Observer. And if you got this sort of larger collection of satellites working together, you could end up with one that could detect the background gravitational waves of the entire universe, that you could see the gravitational waves that were generated by the Big Bang as it was first happening. And that would be amazing. And that's really one of the great dreams of gravitational wave astronomy, because with visible light astronomy, we can only see up to the cosmic microwave background radiation. We can't see beyond that, and that's like 300,000 years after the formation of the universe. But gravitational waves can see through that and see right to the beginning of the universe. So 2030s, LISA, space-based, and there's a bunch of other ideas. The coolest idea for a space-based gravitational wave observatory would have one observatory at the Earth's L4 point, another at the Earth's L5 point, and then another one on the other side of the sun at the L2 point, and that would form a gigantic triangle. And they worked out that if, as long as you were able to kind of move the spacecraft a little bit in their orbit, if you gave them sort of orbits within the L4 and L5 point, you could create this giant 3-sided triangle that was the Earth's orbit of the sun that would always remain the exact same distance. You just have to sort of fine-tune the way the spacecraft were moving, which was kind of an amazing idea. So that would be mind-bending. I can't wait. Alvish asks, what do you think is the biggest possible filter stopping civilizations from advancing? Of course, I have gone on record many times as saying that I think we're alone in the universe. And the reason I think we're alone in the universe is because the idea of the great filter is too horrifying to contemplate. So the idea of a great filter is that you've got these various moments in history that life forms are unable to be able to pass through. So one example of a filter might be the jump to go from single cellular life to multicellular life, right? So if single cellular life is very common in the universe, but multicellular life is very rare because you've got this filter, and that's a filter that we have passed, right? We have multicellular life, so we have passed that filter, but there could be other filters in our future. An example of a filter in our future might be that we create artificial intelligence and the artificial intelligence wipes us out, or we all decide to live in a simulation because it's better to live in virtual reality, or ecological destruction, or an asteroid impact, or something that we can't envision. And when I think about the great filters that lie in front of us, if life is common, and if civilizations have all run up against this great filter and failed, then what that means is that the great filter is impossible to predict. That it happens inevitably, and that you can't predict it in advance, and you can't prevent it, and you can't prepare for it, because nobody has ever done it. And that's a really scary idea, that there is some event waiting for us in our future that is existential, that will prevent humanity from becoming a spacefaring civilization. And we are what? 100 years away from that, right? 200 years, 1,000 at the most, from being able to send spacecraft to other worlds. And, even something as simple as self-replicating robot probes to other worlds. We could be, it's going to happen very soon. And yet there's this event that happens to every civilization, and they wipe themselves out. So which is it? The answer is that we can't know. We can't know what the great filter is, because if we did know, then we could prevent it. And because no civilization has been able to get past it, we won't either. And so when you ask what your question, what is the biggest possible filter? If the great filter is out there, then it is impossible for us to discover what it's going to be until after it's already happened to us. Yeah, which is horrifying, right? So we're alone in the universe. We're the first. That's la la la. I'm not listening. That's part of the reason why I have my position, is because the great filter, the idea of the great filter, is sort of really nasty. Gwym asks, if space-time is the same, why do we generally only refer to it being long ago and not far away? This is the kind of thing that catches new space communicators, which is that for stuff that's fairly close, like the sun, right? The sun is 150 million kilometers away, or it's 1 astronomical unit away, or it is 8 and a bit light minutes away from us. So it takes light about 8 minutes. But the distance that the sun is and the time it takes for the light to get to us are equivalent to each other. And so it makes sense to be able to describe those. Then the same thing goes for anywhere that you could look at here in the Milky Way. If I look at, say, Betelgeuse, and it is 650 light years away, then it is a distance that it takes light to travel 650 years. But when I look at places that are starting to expand away from us, especially as you go all the way out to the edge of the observable universe, then the time the light has taken to get to us is different from the distance that the object was when the light was emitted, and is different from the distance that the object would be now if you could see it in real time. So the classic example of this is it's called the co-moving distance, but essentially the size of the observable universe. If you look at the cosmic microwave background radiation, which is 13.7 billion years ago, the light that was released from the universe at every point in the universe has taken 13.7 billion years to make the journey from wherever it was released to our eyes. And yet, if you were to measure the distance, like if you actually grab a yardstick and measure the distance to that light where that place is, you would measure 46.5 billion light years to get there. So how can light have been traveling for 13.5 billion years, but it's 46.5 billion light years away in distance? And the answer is that the universe itself has been expanding, and these things have been moving. And so where it was when it gave off the light is different from where it is today. And so the rookie mistake that space communicators make is they say that something is far away, and that's how far back in time it is, and those two are the same, and they're not. And so astronomers, they talk in terms of a thing called redshift. And redshift is sort of a way of measuring how far the wavelengths of light have been stretched out by distant objects as they're moving farther and faster away from us. And the maximum redshift, the cosmic microwave background, I think they call it Z is like Z equals 1,000, I think, is the cosmic microwave background. But then even really close, much closer than that, they'll measure a number like Z equals 1. And that's still really far. And so they will measure objects in the universe by how much that light has been shifted into the red end of the spectrum. And that's their yardstick. And they don't care, really, about how far away they are or how long away the light has taken or any of that. They care about how far the light has been shifted, because that helps them figure out at what point of the universe they're seeing this object. Closer to the beginning of the universe, closer to our current day, that's what they look at. So it's a tricky thing to try to explain this, and you have to be really careful about how you say things when you're talking about distance and time in the universe. Cybercharged. Is any future interview with Isaac Arthur planned? I guess. I mean, we've talked a bunch. We've done like 3, I think, interviews on my channel, a couple of interviews on his channel. We've done some collaborations. So yeah, if you want me to talk to Isaac Arthur again, I'm down with that. But you should definitely check out Isaac Arthur's channel. This is going to be a pitch for Isaac Arthur's channel. If you are into futurism, terraforming, sending ships to other star systems, interacting with aliens, uploading yourself to the Matrix, you should check out Space and Futurism with Isaac Arthur. He's just cornered the market on it. Neurostream asks, how many sols is Ingenuity expected to tag along with Perseverance with its solar battery and heating constraints? How many pixels does that rotorcraft's camera have? So Ingenuity is the tiny helicopter that is bolted on to the Perseverance rover, which is like the coolest thing that's been attached to a spacecraft, right? That you're going to have this nuclear powered twin of Curiosity, which is already a marvel with Perseverance, but it's going to have all of these tools on board to be able to search for life on Mars. And then at the same time, it's going to have this tiny little helicopter that's sort of cuddled up under its wheels. It's going to take the thing out, deploy it on the ground, drive away, and then this helicopter is going to fly on Mars. It's got solar panels on it, so it's going to launch off the surface of Mars. It's going to fly around. It's going to try to take a bunch of pictures, land for however long its battery will last, and then it's going to recharge with this solar panel on board. Then when it's got enough charge, it's going to try to do another flight. How long will it last? Well, have you ever flown a drone? Like, it's going to crash on the first flight. Come on, right? It's going to be doing this completely remotely, automated. There's no way they're going to get 2 flights out of it. But no, seriously, I don't know. I don't know. We are in completely new territory with a helicopter on Mars. It's a mind-bending accomplishment. And I think that, one of the problems that we've had, I think I might have mentioned this last week or somewhere else anyway, is that there's a lot of really great ideas. If you go back and look at old NASA technical documents, they've been thinking about airplanes, helicopters, single stage rockets, things like the Starship have been thought of by NASA. They've been thinking about artificial gravity. They've been thinking about different kinds of propulsion systems for decades, for like 50 years. If you go back looking through old NASA proposals, it's incredible what ideas have been thought of. But the problem is that when you introduce an idea with some level of technological risk, you have a chance of destroying your spacecraft, of ending the mission. And so it's always this balance. If you want to get science done, you want to be on a very dependable platform. You want the old reliable 486 as opposed to a modern, Threadripper. Right? As your computer, even though you could get a lot more work done with a Threadripper and a 60 megapixel camera, they go with something that's smaller and safer and dependable. And the same thing goes with alternative propulsion systems and things like that. There was this launch that happened yesterday. SpaceX launched 143 CubeSats And there was all kinds of ideas on it. There was some military stuff, some educational stuff, some research, some NASA stuff. It's tons and tons of little, and we've been reporting on all kinds of ideas. And I love this age. I think one of the biggest boons that we're going to see in the next coming decade is we're going to see cool ideas that have been waiting for the launch prices to come down, will finally get tested in space. That has never been happened before. I mean, it took like 20, 30 years from when ion engines were first developed and proven to work to when they were actually able to fly in space on Deep Space One. It takes a long time. So the fact there's a helicopter on Mars is incredible. And whatever it does, like if it flies once and crashes, it will be incredible. And kudos to the team for thinking of the idea, getting it built, getting it on Mars. I can't wait to see what happens. And we're only like 3 weeks away from Perseverance arriving at Mars. So Arjun asks, how long would Starship be in service before NASA started incorporating it into mission plans? It's a good question. I think Starship has a bunch of issues, not like problems with it, but the way it's been designed and developed that are going to be not very compatible with NASA for a very long time. NASA, with the loss of 2 space shuttles, NASA is very against any kind of launch vehicle that doesn't have an abort system, both a pad abort system, a in-flight abort system. They learned the hard way that you need to have some way to be able to have the astronauts abort, and the space shuttle didn't have it. It would have saved the Challenger crew. It wouldn't have saved the Columbia crew, although maybe if they had realized what was going on as the shuttle was flying up, they could have aborted. So the problem with the Starship is it doesn't have an abort system. It just, on the pad, I guess if there's a problem with the Super Heavy, then the Starship itself could blast with its rockets and get away from the Super Heavy before it detonates. Once you're in flight, again, if there's a problem with the Super Heavy, then you can get away from it. But once you are in flight, the Starship is the rocket. So, and then of course the way they land is sort of terrifying as well. So I think that we're going to have to see dependability for a long time, where these things are taking off and landing and taking off and landing. And then, like they do, NASA will put on scientific payloads, and then they'll put on payloads, cargo flights to the International Space Station and things like that. And then maybe later humans. But I'll bet we're going to see flights with humans to Mars from SpaceX before we see NASA putting astronauts on board Starship. That would be my guess. João de Carvalho. How dangerous is the Kessler syndrome? The Kessler syndrome is not as dangerous as people have sort of led us to believe. The idea of the Kessler syndrome is that you end up with this, as more and more satellites are launched, they're colliding with each other, they're tearing each other apart, and you're sort of filling space with shrapnel. And that sounds terrifying, and that any spacecraft that tries to launch is going to have to go through this sort of churning buzzsaw of space metal, and will just get added to the shield that is blocking spaceflight. But the reality is it's more like friction, that more and more stuff that launches, there's more debris up there. You're going to have to aim more carefully to get through it. So it's not catastrophic, but it's just going to be like another cost of going to space. All right. That wraps up the show, I think, for this week. So if you want to get a single comprehensive resource for space news, you'll want to subscribe to my weekly email newsletter. Every Friday, I send out a magazine of space news with dozens of stories with pictures, brief highlights about the story, and links so you can find out more. Go to universetoday.com/newsletter to sign up. It's totally free. And did you know that all of my videos are also available in a handy audio podcast format, so you can have the latest episodes as well as special bonus material like interviews with me show up on your audio device? Go to universetoday.com/audio or search for Universe Today on iTunes, Spotify, or wherever you get your podcasts, and I'll put a link in the show notes. Thanks everyone for watching here and on Twitch, and to everyone who asked a question. If you want to ask a question for an upcoming show, you can post it in the YouTube comments or in Patreon, or you can join me live on my YouTube channel every Monday at 5 p.m. Pacific time. Thanks to all the moderators, and a special thanks as always, Chad Weber and Nancy Graziano. and we'll see you all next week.